let's talk a little bit more in depth about conductors and non-conducting spheres. In this case, we're going to talk about conductors in electrostatic equilibrium. A charged conductor, such as a charged metal electrode, is in electrostatic equilibrium. Thus, no current can flow through the conductor and the charges are all stationary. This is what's important. The electric field is zero at all points within a conductor if it's in equilibrium. If that were not true, the electric field would cause the charge carriers to move, and thus the charge would not be at rest. So what this means, this is really important. At the center of our conductor, the electric field is zero. Very important. So the electric field, all the excess charges are going to lie on the surface of that conductor. So the electric flux through that Gaussian surface must be zero. However, if the flux is zero, then the Q enclosed is zero. There'd be no charge within the cell. But there's no charges. So on the interior of that conductor, all of the charges are going to reside on the exterior surface of this. So this is what we've just been talking about. Don't get confused about this. All of the charged particles lay on the surface of this. On the inside of that conductor, the electric field is zero, because if we look at these, all these points of these electric fields will cancel each other out. The electric field always is perpendicular. Make sure you know that these are going to be perpendicular to the surface. And the Gauss's law enables us to calculate that surface. And so if I wanted to calculate the electric field on anything such as this through a conductor that has flux only on its outer face, just like we did before, I want to pick a little Billy cylinder to take this path on this. But because this is a conductor, the electric field is only going all out of that one plate. On the inside of this thing, my electric field is zero. And so again, I'm going to use this idea of surface charge density, which is charge per unit area. Gauss's law says Q enclosed equals epsilon naught, well, hell, I forgot what this. Q enclosed is going to equal to epsilon naught times flux. Q enclosed is going to equal the integral of E dot dA. And so my area here is just going to be the area of that surface of that cylinder that I'm going to use. My Q enclosed is sigma A equals epsilon EA. So these cancel. And so that electric field is going to equal to that sigma over that epsilon naught, which is what that says right there. Okay, again, main things, main ideas. Again, you might not understand this conceptually until you hear this about 15 times, but this is what you need to know. Inside a conductor, the electric field is zero. You need to know that the charge is on the surface of the conductor, and that electric field is perpendicular to that surface. So big main three ideas right there. Suppose a charged conductor has a hole in it. Can there be a charge on the interior surface? If we use the Gaussian surface around the hole but within the conductor, the electric flux through that Gaussian surface is zero because the electric field is zero inside that conductor. Thus, Q enclosed is zero. So there is no net charge inside a Gaussian surface, and thus there's no net charge inside the hole. Any excess charges is on the surface of that conductor. Since there's no electric field inside the conductor, no charge inside the hole, the electric field in that hole must also be zero. Okay, an electric field can be excluded from a region of space by surrounding it by a conducting box. So in this case, we're going to have a parallel plate capacitor, and we're going to put a conducting box. And so when we do this, this positively charged electric field is going to induce a negative charge on this surface. This negative side is going to produce a positive right there. And so we call this screening like that, and that is a practical application when we talk about capacitors, which are about the third year of engineering, electrical engineering, you'll get into this. Charges inside a hole within a neutral conductor. So now we're going to have a conductor, we're going to have a hole in it, but now we're going to put a silly point charge in there that has a positive charge. What's going to happen? The electric field inside the conductor is 0, but the electric flux to the Gaussian surface is also 0. So what's going to happen is we're going to have a positively charged object. It's going to induce a negatively charged along this surface right here. But notice, since this electric field has to be 0, we're going to have to induce some positive charges on this outer surface. And so when we totally add up those positives and negatives, my electric field here is 0. Okay? And so, putting it all together, and we're going to work a problem like this, and hopefully it'll make more sense. The electric field is 0 at all points within the conductor. The electric charge is on the surface of that. The electric field is always perpendicular to that surface and has a value of sigma, remember sigma on the AP test, over epsilon naught. The electric field is 0 inside within any hole within a conductor unless we place a charge in there. You're going to see an AP problem like this here in a second that you have to do, so let's work this one together and hopefully it'll make a little bit more sense. So what we've done is we've taken a cross-sectional area, chopped it in half, of a metal shell which has an inner radius r. A point charge of -5 microcoulombs is located at distance r divided by 2 from the center of the shell. If the shell is electrically neutral, what are the induced charges on the inner and outer surface? And are those charges uniformly distributed? What's the pattern inside of this shell? Okay, so basically what we see is we see this shell, this metal shell right here. You should know that the electric field inside of there is 0. You have to know that first of all. So then we got to think, what's going to happen? Well, I know if I placed a positively charged object here on the end, it's going to repel the best that it can to get as way as possible. But we're not in the center here. We are off to this side. And so what's going to happen is there will be the charges. And where the positives and negative charges are, they're inside this metal, because a lot of metals have all these free charges. So these are where they can move. And so what's going to happen is this negative is going to make an accumulation of all these positive charges that are in this metal right here. And there'll of course be some over here just because there's lots of charged particles in here. But it's going to be centered over here on this side closest to this negative. Now, what happens though on this surface of this shell? On the surface of the shell, I have to have negative charges. And so because this electric field is 0 inside of here, the number of the positives and the negatives have to cancel each other out. So I'm going to have some negative charges, and of course that electric field has to be perpendicular to the surface anywhere along here. So I'm going to draw these little negatives. And so the question here is, and this is where you're going to have questions on, is that the positives are going to accumulate here, but the negatives are going to be uniformly distributed. Positives are going to be surrounding this negative charge. The negatives on that outer surface are going to be uniformly distributed. And so why is that happening? One, because the shell is spherical, those electrons are going to distribute out. Distribute out so that the electric field cancels with the positive charges. And those negative charges want to repel, and so they will extend as far apart as possible. And so again, this is going to say, oh, this doesn't make any sense. And if y'all were here, y'all ask me 5,000 questions, and I'd try to play it off like I know what I'm talking about. But basically, all I can tell you is this: what happens. The positives are going to accumulate on the inner surface because it's closer to this. The negative charges, because I know outside of this conductor, I have to have the charges distributed uniformly on the surface. We will get a diagram that looks like this. And so in order for us to draw our electric field lines, remember this is negative, and I'm going to have these positive charges here, so I'm going to have to draw a bunch of arrows like this. And remember, the arrows are drawn from the positive into the negative. And so I'll have some arrows here. We have to have more arrows on this side because there are more accumulation of these positive charges on this surface. Now, do I draw any electric field lines on the inside of the surface? That's a big fat no, and one of the AP problems you'll have to do this. Why is there no electric field lines inside that surface of that conductor? Because the electric field is 0. Will there be some electric field lines coming in? You better believe it. And if you'll look at my picture up above, I did a big fat no-no. Why? Because those arrows are going the wrong direction. The arrows have to go from the positive to these little negatively charged spheres right here. And so this whole diagram, you'd be getting points off because the arrows have to be pointing in. Okay? And so main things I need for you to see. The electric field is not uniform inside the center because this charge is not in the center of the sphere. It's to one side. So my electric field is going to be stronger closer that we are. Inside the conductor, the electric field is 0, so I'll have no electric field lines on the inside. On the outside, I will have some electric field, and it will point towards the surface of that as shown. Some shell theorems that maybe make some sense to you, maybe it doesn't, I don't know. Let's read through this together. A shell of uniform charge attracts or repels a charged particle that is outside the shell as if the shell was concentrated on the center of the sphere. And so as we look at that, a thin uniformly charged spherical shell with 2 charges Q in cross-sectional area. We have 2 Gaussian surfaces, S1 and S2 are shown in the surface. S2 encloses the shell, S1 closes the empty of the shell. So depending upon where it is, we'll make our Gaussian surface to do what it is. If a charged particle is located on inside the shell of the uniform charge, there's no electrostatic force on the particle from the shell. And our third one we're going to talk about here is a non-conducting spherical distribution. Anytime you see non-conducting, you can think of the charges throughout the entire thing. And so as we have to apply this, it's going to be a nest of concentric spherical shells. And we're going to have to use this volume charge density, but the volume charge density will respect to little r, which is the radius density of this. We have worked this problem before. And when we have a non-conducting, and this is the key word you need to see here, we're going to have an electric field on the inside of this because there are charges that are going to be on side here. And so our Gaussian surface are these little bitty spheres. And what you will have to do is you'll do charge per volume. The total charge per charge volume will be my Q enclosed divided by my volume enclosed, or my volume of my Gaussian surface. And when we see this, we will use this ratio, 4/3 pi big R cubed over Q enclosed over 4/3 pi little r cubed, with this little r being our radius of our Gaussian surface. And then of course when we apply that into Gauss's law, some of that r's will cancel each other out. Okay, and that is it for that. We'll start working some free response problems and continue on with the next part a little bit later.